when we talk about a sound wave, sound needs a medium to travel through. And sound, okay, has a lot of the same properties that light waves do. A wavelength is the exact same thing as it is in electromagnetic waves. So the wavelength has a start, and when we get back to that actual start position on that principal axis, that's one wavelength. And sound travels in waves. Okay, so these two really important organs that we have in our body, these sensory organs, who are in charge of getting a tremendous amount of stimulus. Okay? They both use waves. They just use them in very different ways. Your eyeball, okay, your cones and your rods, the receptors in your eye, they get stimulated by light waves. So different frequency waves mean different colors. Okay, brightness, that's the cones. Low light, that's the rods. Okay, and what happens to your pupil? It gets bigger in the absence of light. It gets smaller in bright light. Okay, all that stuff is true, but the ear works a slightly different way. Because sound can only travel through a medium, sound is vibration. Sound, there's actual physical, visible proof that vibration is occurring. You just put your fingers on your actual voice box or on the surface of your throat here, and you actually just hum, or you make and you can actually feel the vibration. Okay, you can. And that's because sound waves, because they have to travel through a medium, create a physical, actual vibration. And it's the propagation of that vibration, which means it sets off a chain reaction inside your ear. Okay, it starts with the outer part of the ear, and it hits your eardrum, which then starts to vibrate, which causes something sitting against it to vibrate, which causes something else, until you get to the auditory nerve. So, in a way, it kind of works like the eye, but it's also quite different because there's parts of your body here that are physically vibrating and moving because of certain sound waves. So just like when we talk about visible light, the amplitude of the wave is going to have actual meaning here. And if you remember, the amplitude is the height of the actual rise, okay, of the actual wave. Now, the wavelength in sound, okay, so wavelength in light was color. So if we look at this and we do a table here versus light and sound, and we compare waves, we'll see that there's some actual similarities there and there's some differences. For a wavelength, for light, it demonstrated color. Red wavelengths were much longer than blue wavelengths, right? Well, for sound, we're actually talking about pitch here, about the notes. So the lower the notes, the longer the wave is. The higher the notes, the shorter the wave is. If we look at the two different wavelengths here, and I know they're not really well drawn, but that's okay, they both have the same amplitude. But the red line, the red wave, is much shorter. Therefore, they're going to be at the same volume, but they're going to be completely different notes. The shorter the wavelength, the higher the pitch, the higher the note. The longer the wavelength, the longer the space for one wavelength, the lower the note. Okay? Now, height of amplitude is a little bit different. So when we talked about amplitude in light, we talked about the shades of the colors. a really high amplitude had a really dark shade. So in this case, amplitude in sound has everything to do with the volume. The higher the amplitude, the greater the volume. So my pitch here stays the same, but my volume actually changes. The lower the actual volume, okay, same wavelength, in this case you've got a lower or a smaller amplitude. So in sound, amplitude deals with the volume, and wavelength deals with the actual pitch. Whereas in sight, okay, wavelength deals with color, and amplitude deals with shade. Okay, so dark blue versus light blue. All right, blue versus red for sight. And then for sound, low sounds versus high sounds. And louder things versus softer things.